All right, this is the review for the final exam. Number one, section 5.2, binomial probability distribution. A certain chain of coffee shops has a 58% recognition rate. We sampled 10 Coffleton residents. What's the probability of exactly 4 recognizing the name brand? All right, X is equal to 4, trials at 10, probability of success 0.58. Whenever we need the exact, all right, find a probability of an exact number of successes, we use binomial PDF. 10 trials, 58% recognition rate, X is 4. Hitting calculate, my calculator returns 0.130, letter A. Number two, test consists of 10 true false questions. Already I know the probability of a success is 0.5. The problem won't tell me that, but we understand that. It's like flipping a coin, 0.5. Heads and tails, true, false. To pass the test, the student must get at least 7 correct. What's the probability the student will pass? All right, at least 7 is x greater than or equal to 7, which is 7, 8, 9, or 10. Yes, I could solve for probability of exactly 7, solve for the probability of exactly 8 and 9 and 10 and add these 4 together, but I would much rather find the probability of the complement, which is 0 all the way through 6, and then subtract that from 1, and then I'll have what I'm looking for, 7, 8, 9, or 10. So the first thing I would do is put 1 minus, then I would go to binomial CDF. All right, 10 trials, probability of a success, 0.5. I'm looking for exactly 6. It's going to add the probability of 0, 1, 2, 3, 4, 5, and 6, and stop after to get the answer to 6. Then I'm taking this and I'm subtracting it from 1, giving me the probability of 7, 8, 9, or 10 to be 0.172, letter A. Number three, 36% of the adults questioned report their health was excellent. If we survey 14 adults, what's the probability of 3 or fewer in excellent health? Once again, it's CDF, cumulative. 3 or fewer in excellent health, X is less than or equal to 3. 14 trials, probability of success, 0.36. So what I'm looking for is less than or equal to 3x. So that's 0, 1, 2, 3. I like this because I don't need to subtract from 1. I'm finding what we refer to as the front end, right? There's no need of any subtraction, and I'm not looking for the back end. So binomial CDF, there's my 14 trials, 0.36 is my probability of success. And I want the calculator using CDF to add the probability of 0 with 1, with 2, with 3, and then stop right after it hits the answer to 3 and add the other remaining values. 0.198 CDF, front end. Section 7.1, find the error, margin of error. Well, there's the formula. You need a z-score associated with 95%, which is 1.96. Theta is given to you as 0.31, and you also know n is 50. Plugging those values in, 1.96 times sigma, that's a theta, times sigma divided by the square root of 50, 0.09, letter C. Number 5, same idea. We're looking for the margin of error. There's the formula. We get a 90% confidence level. 90%, 1.645 times sigma, which is given to me at 2.5 divided by square root of n, and it's 39.7. All right, now we're looking for the complete interval. All right, so I'm going to stat, carrying over to test, and coming down to z interval. I've got statistics. I know my n, I know my x bar, I know my sigma, I know my confidence interval, or level, 99%. Plugging those values in, hitting calculate, then making sure that my answers all have 1 decimal place. So I went to is my mode, and I made sure my mode was set to 1 place. So I wanted this answer to appear right here exact. I don't want to have to play round off by myself. 1 decimal place, spot on. Letter A. Find a confidence interval once again, and sigma is given to us. So we're using z interval. We're going to stat, arrowing over the test, coming down to z interval. I believe it's number 7. And you know sigma, you know x bar, you know your n value, and you know your confidence level, 98%. corrected 1 decimal place, 62.3, and 65.5 on the high end. We're 98% confident that the true mean of the population lies between those two values. Find a minimum size in order to be 95% confident. All right, there's the formula. So 95%, my z value is 1.96. So the formula says take that, multiply it times sigma divided by the error and square that whole quotient. So putting in the 3 values, 1.96 times sigma 11 divided by the error 2, squaring all that and making sure that we round up to the next highest number, 116.2, rounded up to the next highest integer, 117, letter B. Same idea, looking for the minimum sample size. There's my formula. We're looking at a 95% confidence level. There's my z-score, 1.96. Sigma is given to us as 1500 right here. Standard deviation, and the error is 300, within $300 of the mean. Putting those 3 values in, and here's one where it's 96.0. Sometimes they round that up to 97, sometimes they don't. But in this case here, nothing even close. All right, 96 to 97, 166, 136, 68, nothing close. Here it is, letter A. All right, now we're into section 7.2, number 10. Find a margin of error. Sigma is not known. So we're looking with t distributions, t-scores. So here I got my t chart requires, the degrees of freedom. If n is 12, degrees of freedom are 11. Looking up 11 where it corresponds or intersects with 95% confidence interval gives me a t-score of 2.201, 2.201. Plugging in the 3 values, your t-score, you're given S value, standard deviation of a sample, 3.4 divided by the square root of n is given to you as 12. 2.16, exactly, letter B. Number 11, once again, margin of error, section 7.2, sigma is not known. We're using t values. All right. Degrees of freedom would be 1 less than 51, that's 50. Now that corresponds with 95% with a 2 intersect on your chart. You're going to read a t-score of 2.009. Substituting in that value for t, substituting in 203 for s, dividing by the square root of n, which is 51. Hitting calculate or whatever, just pressing enter, 57.1. Margin of error, spot on number 11. Construct a confidence interval. We're still in section 7.2. So I'm coming down to t interval. Now we're given statistics. We're given x bar. We're given the standard deviation. We're given n. We're given the confidence estimation is all contained a problem. I've outlined it or underlined it in red. Pressing enter and making sure I've got my calculator, my mode set to one place because I want this answer to look just like letter D, spot on, where I don't need to do any rounding on my own. 95 values here that are fairly close, but with 1 decimal place, your answer here will match up exactly. Construct a confidence interval. Here again, we're given values now. All right, we have raw data, 1, 2, 3, 4, 6 values. So first thing I do is to put those values into a list. I recommend list 1. So I placed them in. I went to stat, test, arrow down to t interval. Now make sure that data is highlighted. So you would arrow over, press enter. So the data option is highlighted. My values are in list 1. Frequency is always 1. We're told we're looking for a 90% confidence level. Pressing calculate. And here again, these answers are all correct 2 decimal places. Slight discrepancy here. I'm off by 1/100th, and the high end off by 1/100th. There's nothing even close to, well, 72.12, but 72.22 is as close as you're going to get to 72.23, letter D. And finally, section 7.3, population proportion. We're looking for the error. It's a brand new formula. We're back to z-scores. The z-score associated with the confidence level of 98% is 2.33. P hat, the the sample proportion p hat is given to us as 35%. Therefore, q hat is 1 minus that, or 0.65. All right, 35% is a decimal 0.35. Subtracting from 1, you get 0.65 for q hat. Substituting in your correct z-score, 2.33 times. Notice I didn't need a time sign here. This number next to the square root, calculate knows to multiply. Replace p hat with 0.35. Replace q hat with 0.65 divided by your n value, which was given to us as 820. All the answers here have 4 decimal places. I made sure my mode was set to 4. I want my answer to be exact. In that case, letter B. Same idea, population proportion. There's how you calculate the error. The z-score associated with 90% is 1.645. Once again, he tells me what p hat is, 40%. But make sure you use 0.40, not 40, obviously. If that's the case, then q hat is 1 minus 0.40, 0.60. Substituting in the correct z-score, 1.645. I've used 0.4 for p hat. Didn't need to use 0.40. 0.4 is fine. I used 0.6 for q hat. Divided by the n value, 1580. 0.0203, let it be. All right, now we need a confidence interval. All right, so once again, we're going over to stat, arrowing over to test, coming down to one prop z interval. I believe it's letter A colon. It asks us for 3 values. You're given 3 values. You're given an x, you're given an n, you're given a confidence level. Just substituting those values in the correct order. And correct the 3 decimal places, 0.379, between 0.379 and 0.525, exact, letter A. Construct a confidence interval, same idea. Stat, test, arrow down to letter A, one prob z interval. Once again, it requires 3 values. You're given the 3 values. Simple enough to put those numbers into the correct spot. Hit calculate and correct the 3 decimal places. Spot on, 0.5, 0.582 to 0.727. Spot on, letter D. Number 18, find the minimum sample size. Well, when p hat is known, you use this. When there is no estimate, when there is no estimate of p and p hat, actually, it should say. All right, we're using this formula. It should be p hat here. All right, what we're doing here is we're assuming p hat is 0.5 and q hat is also 0.5. 0.5 times 0.5 gives me this decimal 0.25. There's the confidence, there's the x value, z value that's associated with 92% confidence level. And just substituting in my z-score, the formula says to take the z-score multiplied by 0.25 divided by the error, which is given to me as 0.041, and I'm squaring that. Now, he tells us always to round up to the nearest whole number, no matter what the decimal remainder is. All right, in that case there, 455.5, no matter what it was, 455.432, you still would have gone up to one more. Rounded up to 1 digit higher, 456. Still, p hat and q hat are unknown. If p hat is unknown, we're using this formula here. And the z-score associated with 98%, there it is, 2.33. Substituting in place of z, that, squaring it, times 0.25 divided by the error squared. 37,700.7 rounds up to 37,701. Now we're given p hat. It's estimated as 0.16. All right, so not the same formula. See, when we didn't know what p hat and q hat was, we said, hey, let's take 1 divided in half, 0.5 for each of these. This is why the previous formula had 0.25 here. But now we know p hat. The z-score associated with 90% is 1.645. We know p hat is 0.16, therefore q hat is 1 minus that, or 0.84. All right, so there's my z-score squared. 0.16 is my p hat, 0.84 is my q hat, divided by the error. You can't see it here, but it's 0.16 squared. 227.3 rounds up to 228. P hat is given to us as 0.185. All right, so when P hat is known, this is the formula I'm using. The z-score associated with 99% is 0.2575. If Q hat is given to me as 0.185, stands to reason Q hat is 1 minus that, 0.815. Substituting in place of my z-score, squaring it, there's my P hat times my Q hat divided by my error, which is error is given to me as 0.008. You're not seeing all this and all that, but I'll be putting it in and squaring it, going by the formula here. 15,620.8 rounds up to 15,600.